Okay, so this lesson starts our unit on similar figures. And specifically, we're talking about dilations. We're going to perform and define formally what the heck dilations are. And we've seen dilations perhaps in another math class about making a figure either bigger or smaller. Maybe we've gone to the eye doctor and gotten those little drops that they put into our eyes to dilate our pupils so that they can look inside of our eyeballs and see all the problems with it. Or maybe no problems, whatever. Okay, so before we get started on the actual lesson, let's go on a web exploration here. So pull up the web browser. I am on this 17.1 Dilations webpage. To get there directly, if you click on geometry, this is under, down here at the bottom, it says O3A, Dilations and Sim. I'm going to tap on that one, and you can see 17.1 is the first one that's listed. All right, and then once I'm here, of course, there's the lesson notes and the answers. Here's a link to GeoGebra, and we are going to do that as an investigation in this lesson shortly in one of the other videos. And then what I would like for you to do, if you have access to a printer, is to actually open up and print out the dilations handout. If you don't have access to a printer and you can't print this one out, that's okay. You can still participate in this lesson. You will just need some graph paper. What? You don't have graph paper either? Okay, then get yourself maybe a straight edge, a ruler of some kind, and a blank piece of paper, and you can start drawing yourself some graph grids. Okay, so and one other thing on the website is if I scroll down a little bit more, that's where you're going to find the homework instead of right beside the lesson notes like we normally see it. So there's our challenge problems. There does, you need your compass and straight edge for one of the problems on there, actually two of those problems. And then look, it's just 3 problems. We can handle this, totally can handle this. All right, let's go back to the lesson here. And here's the slide, which we kind of saw on the web page here for our objective, being able to perform and define dilations. And dilations, definitely something that Ant-Man, if you're familiar with the Marvel Universe, does, getting bigger or smaller, because dilations go in either one of those directions. Now, we've seen this picture before as a warm-up question, and it was which of these sets of spoons do not belong? And you might remember that whenever we answered that question, it was dilations. Dilations didn't belong. Why didn't they belong? We've got translations, reflections, and rotations. All of those things were examples of rigid motions, but dilations were not. Dilations, you're making your shape bigger or smaller, and so it doesn't preserve the size and the shape of your figure here. All right, so we had talked about informally transformations as just being some sort of operation that changes some aspect of our geometric figure to produce a new figure, and that could be something like translation, rotation. I can stretch it, I can shrink it, but the figure that we start with is called the pre-image, and the figure that we end up with is, of course, called the image. How do I tell the difference whenever I have a set of pictures? Well, it's usually the image that has those little prime markings, as we see here in the little picture, that one is the new figure, and this point A is where it originally came from. So again, when we were talking about transformations, we broke those things up into 2 separate categories, the ones that were rigid motions versus ones that were non-rigid. The rigid ones, we've done extensive work on rotations, on reflections, and translations, both in and out of the coordinate plane. And the main thing about rigid motions, of course, is that they preserve the size and the shape of your figure. Your image and your pre-image are congruent to each other. And as a matter of fact, that's how we first learn to define congruence formally, is that if you can come up with a composition of rigid motions that maps one onto the other, we can prove that they are congruent to each other. That is not true over here on the right-hand side for these blueberry-flavored ones instead of these strawberry-flavored ones. We've got dilations, we've got stretches, we've got shrinks. So when we talk about stretches and shrinks, that's usually just in one direction. Dilation, though, is all over, and that's what this lesson in particular is all about. So before we hit our dilations, just kind of recap something that we've done before in the coordinate plane. And we've got ourselves a coordinate mapping. Use the coordinate mapping x comma y gets mapped to x plus 8, comma, y plus 3 to translate triangle SAM to create triangle S prime, A prime, M prime. So if I just take a look at the coordinate mapping there, I'm adding 8 to my x's, I'm adding 3 to my y's, and that's going to translate, as it says here, it's translating, but specifically 8 units to the right and then 3 units up, point by point. And so here is where I end up. Now, as far as this goes, remember that this is all controlled by, translations are controlled by a vector, and that vector I can show you here on Notability where I can write on the screen. There we go. So this vector is essentially 8, 3, which means from any point, move it right 3, move it right 8, and up 3. If I were to connect, let's say, the point M to M prime, or let's say in S to S prime, those two directed line segments are exactly the same length and they go in exactly the same direction. That's how we formally defined what a translation is all about. We're going to do the same kind of thing with dilations. Now you can break this vector down into its horizontal and vertical components. The horizontal component down here, of course, would be 8 units to the right, and its vertical component there would be 3 units up. Okay, just a refresher of some transformation stuff that we've done in the past. But this lesson specifically is about dilations. So a dilation, instead of just, say, scooching left, right, up, and down, and reflecting and rotating, a dilation is a type of transformation that's going to either enlarge or reduce our figure. Anytime we perform a dilation, we need 2 pieces of information, and those 2 pieces of information are a scale factor, which, as we're going to see, is going to tell us how much bigger or how much smaller our shape is going to get, and we also need a center of dilation. As you can see in this little picture here, the center of dilation is the point that we're going to dilate away from. Okay, in the next video, I'm going to take you through a GeoGebra investigation where we can play around with a dilation dynamically and really kind of understand and wrap our heads around what the scale factor is all about and what this center of dilation is all about.